This video is an introduction to the force of friction. In this video, we're going to be looking at two different types of friction. Friction is a force that acts between two surfaces that are in contact with each other. And the two types of friction, static friction versus kinetic friction, have to do with whether those two surfaces are moving relative to each other or not. Static friction is when there's no slipping between the two surfaces that are in contact with each other. Kinetic friction is when there is slipping between the two surfaces. The one object is sliding across the other object. Again, when people first see the names, static friction makes them think that the object is not moving. That's not exactly true. It's that there's no slipping between the two surfaces that are in contact. There's no relative motion between the surfaces that are in contact with each other. So let's look at this example to understand these forces of friction. If I have a box that's sitting on the ground and I don't push on the box and the box is not moving, then we know that no friction force is needed to keep the box stationary. But let's say that I start to push to the left on the box and the box still doesn't move. Well, that means that there had to be something that was keeping the box from sliding. So let's say that I push to the left with a force of 5 newtons, then static friction had to be acting to the right with a force of 5 newtons as well to keep the box stationary. And maybe I increase my force. Now I apply a force of 10 newtons to the left and the box still doesn't slide. That means that the static friction had to get bigger. The static friction had to also be 10 newtons to keep the box from sliding. And I increase my force even more. Now maybe I'm applying a force of 15 newtons and the box still doesn't slide. That means the static friction got even bigger. So static friction can get bigger and bigger and bigger, and it's as big as it needs to be to keep the box from slipping. And notice that the force of static friction is parallel to the surface that the box is in contact with. It's parallel to the ground. Friction is always going to be parallel to the two surfaces that are in contact with each other. So I applied this force. My force was getting bigger and bigger and bigger. The box wasn't sliding, so that meant that the static friction was getting bigger and bigger and bigger. But we know that at some point the box is going to start to slide. So if I keep increasing my force, I eventually reach a point where the box starts to slide. So let's say that I was applying that 15 newtons and the box didn't slide, but maybe I make my force just a little bit bigger. I apply a force of 15.1 newtons and the box did start to slide. Well, now that it's sliding, we've switched from static friction to kinetic friction. We're going to see that the kinetic friction force is going to be smaller than that maximum force of static friction. So this shows that there's an unbalanced force that's acting. The box is going to accelerate. And now if I want to keep the box moving and I want the box to move at a constant velocity, then I can adjust the force that I'm applying. I make it a little bit smaller, and if the force that I'm applying equals the force of kinetic friction, then the object will keep moving at a constant velocity. Notice in this situation, it's not that a force is needed to keep a box in motion. It's that no net force is needed to keep the box moving at a constant velocity. And this is what caused a problem when people were first trying to understand motion. They thought if you stop pushing on something, it slows down and stops. And it does, because usually the thing that we're looking at has friction. And so we have to keep pushing on this box, not because a force is needed to make something move, but because there's a force of friction that's also acting, and I need my force to balance out that force of friction. So now let's focus on static friction. So the static friction force is going to oppose whatever force is being applied until the object breaks away and starts to slide. And so there's two different ways that static friction can come up. The most common way is this first case. We apply a force to an object, and static friction also acts to keep the object from sliding. So I'm applying a force to the right, static friction is acting to the left, keeping the box from sliding. And the static friction is going to oppose the component of the force that I apply that's parallel to the surface of contact. Again, the static friction acts parallel to the surface of contact, and so it's canceling out the parallel component of the force that I apply. The second case is the one that's a little bit harder to see at first, but you could have two objects that are accelerating together. So here, think of a cup that's being dragged by a piece of paper. But if the cup and the paper are both moving together, they're both accelerating to the right, then the thing that makes the cup accelerate is the static friction between the cup and the paper. So here, the static friction is needed to keep the object from slipping against the surface. The cup has inertia. If it's at rest, it wants to stay at rest. That would mean that it would be effectively sliding to the left relative to the paper. To keep the cup from sliding against the paper, static friction pulls the cup along with the paper, making the cup accelerate to the right with the piece of paper. And so we saw with static friction that the force of static friction can get bigger and bigger and bigger until we reach some point when the object starts to slide. There's some maximum value that the force of static friction can have. That maximum value of the force of static friction is given by the equation: the maximum force of static friction equals mu sub s. It's the Greek letter mu, mu. Mu sub s times the normal force. Mu sub s is called the coefficient of static friction. It's a unitless quantity, and it describes the roughness of the surfaces. The rougher the surfaces are, the larger that coefficient of static friction is. So the maximum force of static friction equals the coefficient of static friction times the normal force. Again, the normal force is how hard the two surfaces are pushing against each other. The important thing to note, though, is that static friction is not always equal to its maximum value. In the example that we just talked about, the static friction at the beginning when I wasn't pushing in the box was 0. And then that force got bigger and bigger and bigger. So the static friction was just as big as it needed to be to keep the object from sliding. And it can get larger and larger and larger up until this maximum value. So the way that we often describe that is that the force of static friction is greater than or equal to 0, and it's less than or equal to its maximum value, the coefficient of static friction times the normal force. So it can be anywhere in between those values. It can be as small as 0 if no friction is needed to keep the object from slipping, up to some maximum value. And now let's look at the idea of kinetic friction. So once we have applied enough force to make the object start sliding, we now switch to kinetic friction. So when the object is slipping against the other surface, we have kinetic friction. And the force of kinetic friction is a much simpler idea. Instead of having a range of values that it can be, the force of kinetic friction has a specific value. The force of kinetic friction is given by the coefficient of kinetic friction, mu sub k, times the normal force. Again, mu sub k, that coefficient of kinetic friction, is a unitless quantity. Again, it still describes the roughness of the surfaces. So the force of kinetic friction depends on this coefficient of kinetic friction, and again, it depends on the normal force. It depends on how hard the surfaces are pushing against each other. But instead of this being a range of values, the force of kinetic friction equals this coefficient of friction times the normal force. So if I look at that situation with the box that was sitting on the table, and I apply a force that gets bigger and bigger and bigger and bigger, then the force of static friction is getting bigger and bigger and bigger and bigger until I reach the point where static friction was maximum. When I reach that maximum value of static friction, the object starts to slide. And once it starts to slide, we switch to kinetic friction, and we have this constant force of kinetic friction. The coefficients of friction are experimentally determined properties of the two surfaces that are in contact with each other. And so these are things that have to be experimentally determined, experimentally measured. And so for something like rubber on concrete, the coefficient of static friction is around 1. The coefficient of kinetic friction is around 0.8. Again, these are kind of average values. It depends on the rubber, it depends on the concrete, how rough the concrete is, but this is just kind of a typical value for rubber on concrete. If you have steel on steel, it depends on, is it just the steel rubbing against itself, or do you have some type of oil or some type of lubrication in between the two pieces of steel? If there's no lubrication between them, you have a coefficient of friction that's larger than if there is lubrication between them. The lubrication reduces that friction. And so the coefficients of friction are things that are usually going to be given to you in a problem, or they might be something that you experimentally determine as you're doing a problem, or it might be something that you're asked to calculate in the problem based on some situations. And notice that for all of these values, the coefficient of static friction is greater than the coefficient of kinetic friction. This goes along with the idea that we said that the maximum force of static friction was greater than the force of kinetic friction. It takes more force to make the object start sliding, exceeding the maximum force of static friction, than it does to keep the object sliding at a constant velocity. And so just kind of a quick understanding of what is actually causing friction microscopically. So if we have surfaces that are in contact with each other, those surfaces are jagged. There are these rough spots that are catching against each other. And so as the one surface slides against the other surface, those peaks are catching against each other. And it's those peaks catching against each other that are actually causing that friction. And on a more molecular level, you actually have bonding that happens between the two surfaces. And that's one of the reasons that static friction is larger than kinetic friction, because when the objects are not sliding against each other, you have that ability for them to bond a little bit better together. When you're trying to make the object start sliding, you have to break that bond and rip the two surfaces apart. And then the two surfaces are sliding against each other. In the last slide, we talked about the coefficients of friction for dry steel on steel versus lubricated steel on steel. What the lubrication does is it goes in between, it kind of fills in between the two surfaces, and it allows the one surface to float past the other one without as much direct contact. Some of the pieces, some of the jagged pieces will not catch against each other because they're kind of able to float past each other without as much direct contact, which reduces the force of friction. In some later videos, we'll be going through actual example problems with friction.